welcome back to this course on principles of polymer synthesis. In the first class, we have talked about how the polymer science evolved from knowing nothing about polymer structures, yet synthesizing polymers, yet exploiting their properties in the early 18th and late in the early 19th and late 19th century, and even the early 20th century, to knowing precisely what the structures are, to be able to put precisely the monomer units the way you want, and to be able to evolve the properties the way you want with relationship to the structure of the materials. Now, in this class I am going to talk about molecular weight determination of polymers. This is the topic of this class. So, I am not going to start with molecular weight of polymers per se. I am going to start with, as promised towards the end of the last class, the classification of polymers by different ways. So, let me begin with that. So, how you can classify different polymers. Of course, this is different from whatever we talked about when we told commodity polymers, specialty polymers, or when we talked about engineering polymers. Those are different kinds of classifications. Now, you can classify polymers on the basis of their origin. This is something we already discussed in the previous class. So, we can have natural polymers, say for example, polysaccharides. An example could be starch, could be cellulose. We could have natural rubbers or completely synthetic polymers, say for example, bakelite, a condensation product of phenol and formaldehyde, or we can have semi synthetic polymers. Take for example, your cellulose nitrate, about which we discussed a lot in the previous class, and we also talked about the celluloid films that are actually made up a combination of cellulose nitrate and camphor. Camphor plasticizes the material. So, those things we discussed before. So, on the basis of origin, we could have this kind of classification: natural, synthetic, semi synthetic. Also, on the basis of property, we can have polymers which are say thermoplastic. So, these are materials which when you heat they become moldable, and when you cool they becomes more rigid. So, an example could be polyethylene terephthalate. We will talk about that in details when we talk about the synthetic processes. Or we could have thermosets. So, typically these are materials with low molecular weight materials, and these materials, I mean the starting point is low molecular weight materials. So, it is relatively low molecular weight, what you can tell as pre-polymer, and then this material you treat with some reagent, maybe you heat the material also, you heat it and then it becomes set into a particular structure. So, basically this reagent helps it to cross link. So, when you have a cross linked three dimensional extensive cross linking between different polymer chains, so it gets set into this particular structure. So, that is called thermoset. An example could be the reaction of epoxy with amine, and then you have materials where we have cross links. So, those are thermoset materials. And you can also classify on the basis of structures. It could be linear polymer, or you can have some branching of the polymer, or you could have cross linking also. Now, on the basis of structure, there could be another way to classify this. Some say this is also on the basis of mechanism, but typically I can tell that this is on the basis of structure. Say you can have addition polymers, addition polymerization, or you could have condensation polymerization. And finally, on the basis of mechanism. So, addition, condensation, and on the basis of mechanism, you can have step growth polymerization, or you can have chain growth polymerization. Now, we are going to talk about these things later on in detail. Mostly we will talk about this step growth and chain growth polymerization, and some of them can be actually dubbed as addition or condensation, and this kind of classification of step growth and chain growth is better than addition and condensation, this kind of classification here, and we will explain that a little later. Okay. All right. So, before going into further details of this, when we, as promised in the starting topic, start discussing about the molecular weight, I would like to talk a little bit more about addition, condensation, polymerization, and the classification when we do vis-a-vis your step growth and the other one, chain growth polymerization, and then we will come to slowly the other aspects. Say this kind of classification on the basis of structure, addition polymerization and condensation polymerization, this was actually introduced by Carothers somewhere around 1929. So, addition polymerization basically it means that whatever monomers you have, all the monomers get incorporated into the polymer. So, basically the monomeric structure will be the same as the repeat unit structure. Say you take an example, you take ethylene and you polymerize. So, this is the monomer, and then in the polymer you have CH2 whole N. So, the repeat unit has not lost any of the atoms from the starting monomer. So, this is your addition polymer. Condensation polymer basically it is a condensation reaction. So, if you react a diol, say you have a diol and you are reacting with a diacid, you know alcohol and acid react to form esters. So, if you do this reaction, so bifunctional monomers, if you are doing this reaction, so basically you have this kind of polymer that is produced. So, what happens is that in this particular reaction, you see this repeat unit does not have certain atoms that were present in the starting monomers. So, you have a condensation reaction. So, the repeat unit is slightly different in structure than your starting monomers. Basically, here a small molecule is liberated, 2n minus 1 molecules of water. So, that way the condensation polymers are polymers where small molecules are liberated in that particular reaction. Now, a problem with this kind of classification is that this cannot account for all the kinds of polymers. Say if you are looking for polymers which are of the class polyurethane. So, polyurethane, actually I am going to talk about that here. So, polyurethanes. So, you are reacting say an alcohol diol with a diisocyanate . So, then what happens is that, so you so in this particular reaction, you basically have this kind of urethane linkage that is produced, and you see that no small molecule is actually eliminated. So, what do we call this particular reaction? Is this a condensation reaction or an addition reaction? So, typical wisdom suggests that this reaction is slightly different, at least if you talk about the mechanism, than your polyethylene formation reaction. So, this is not a complete way of describing the polymerizations in that case as far as the classification goes. So, in fact, there is another way to describe this kind of polymerizations, that is on the basis of mechanism, which was suggested by Flory, on the basis of mechanism. So, it is either chain growth polymerization or step growth polymerization. So, basically if you are looking at chain growth polymerizations, typically you have this kind of C double bond C units in the monomer, which is a vinyl based on vinyl monomers. Now, these vinyl monomers, when you polymerize, they will create this kind of product. I mean very similar to, I mean if you have ethylene, you have this polymer. So, this is chain polymerization. So, what happens is that you have an initiator that initiates the polymerization process, and then what happens is that the successive addition of monomer units in a chain reaction occurs, and then this particular process is called chain polymerization. The other process is step polymerization, the other mechanistic way of describing the different kinds of polymers. One is chain polymerization, one is step polymerization. Now, step polymerization is basically, most of the condensation polymers are also step polymers. So, as I told you, if you are reacting a diol and you are reacting with a diacid, this diol. So, basically you have a polyester, the structure of which I have drawn previously. Now, this is called step polymerization, because you know the polymerization occurs in steps. Say you create a dimer, diol and diacid react and create a dimer, and that dimer can react say with another dimer and it can create a tetramer, or dimer can react with tetramer, or dimer could react with trimer. So, all these species of different, what you say as molecular weights are present during the reaction, which is quite different from your chain growth polymerization. So, with this kind of classification, then the polyurethanes, they become step growth polymerization and not chain growth polymerization. The reason I talked about this is because next several classes we are going to spend talking about first the mechanistic aspects of step growth polymerization, the dealing with the kinetics of these polymerizations for example, and then we will also talk about chain growth polymerizations, and afterwards we will try to apply these principles in the synthesis of different industrial polymers. But now is the time to talk about the main topic that I am going to deal with in the next few classes. The reason I discussed some of these things at the earliest is because these directly concern with many discussions that we will have later on. Okay. So, we are going to talk about molecular weight. You know, you have done a reaction, suppose you want to create a polymer, Now, several of the monomer units have come together to create this polymer. The polymer that you have got, how do you characterize this polymer? One of the main things that you do is you try to find out the molecular weight of this polymer, and there are different ways to determine the molecular weight, and also I will tell you that the molecular weight is basically an average molecular weight, very unlike the whatever small molecules that we deal with, it is very different. Small molecule synthesis and polymer synthesis, they are very different. So, firstly then we will start with what is molecular weight. So, molecular weight by its very definition, it is basically like this: average mass per formula unit divided by 1/12 of the mass of an atom of 12 C. So, that way molecular weight does not have a unit like gram per mole. You basically tell that as molecular mass has this unit, but still it is quite prevalent that people will use gram per mole for molecular weight, and I do not see any problem in that, because basically that does not change the science that we discuss. But it is important to keep in mind that molecular weight, that way we use something called Dalton. So, you know there is a mass on the up and there is a mass at the on the denominator. So, numerator by denominator. So, basically the unit of the mass gets cancelled. So, gram per mole is the molecular mass, but molecular weight also we use this unit gram per mole, or you can use Dalton also, although this is not correct that way, but we use, this is quite prevalent. Okay. Now, one thing that you should keep in mind is the following: as I was telling, unlike preparation of small molecules, when you are creating a polymer chain, say hundreds of monomer units are coming together through covalent linkage. It is almost impossible to create a polymer which has a fixed molecular weight. In a way, so several chains you are creating by the synthesis, by the polymerization, all these chains will have a slightly different molecular weight because of the inherent statistical process that is there in the preparation of polymers, which will mean, suppose you have 100 number of units in a polymer chain, another polymer chain can have different number of units, maybe 110, maybe 105 or maybe 98. So, like this. So, when you are creating a polymer, you have a distribution of molecular weights in all these polymer chains. So, it is important to recognize that when we talk about molecular weight of a polymer, we basically talk about an average molecular weight of the polymer, and there are techniques through which you can determine this average molecular weight. We will come to that and we will discuss only specific techniques, not all the techniques, some of the important techniques we will discuss. Now, certain things you should keep in mind, that what are we dealing with? We are dealing with this property. What we are interested in is to create the property that we want in the polymer, and what is its relationship with structure. Now, different properties of the polymer, they will vary in different ways with the molecular weight. Say one of the properties that are very important that I want to talk about here, say material strength. Versus say molecular weight. It will be something like this, say point A, point B, point C. So, if your polymer is of very low molecular weight, then you do not have this kind of material strength. So, somewhere here if you have molecular weight, your material strength is not good enough for any kind of industrial application. So, you need at least a certain molecular weight, so that the properties they have started to evolve, and this is typically, again these are approximate, say between 5000 to 10,000. So, at least you need this kind of molecular weight in order to get certain properties that become relevant for applications, and after that they may become slowly saturated, so on and so forth. So, from this discussion also, then it is important to understand that ultimately what we want is that we want a distribution, we want to know what is the distribution of molecular weight in the polymer sample that we have prepared. Now, we will come to that after. First, let us talk about this thing, average molecular weight. So, when we say average molecular weight, there are different kinds of averages that we deal with. One of them is number average molecular weight, which we can designate as MN bar. This is number average molecular weight. And then we can have what you call as weight average molecular weight. we can have viscosity average molecular weight. These are some of the main molecular weight averages. Now, if you are actually trying to find out say Mn or Mw or Mv, you are basically using different kinds of experiments in order to determine these different molecular weights. So, let us say we before we come to the different experimental parts, let us try to have an expression of these, means what are the expressions of these different averages. So, when you talk about Mn, number average molecular weight, it is basically total weight of all the molecules in the sample, all the molecules in the samples divided by total number of moles, total number of moles. So, which is nothing but W, which is total weight divided by say total number of moles. So, all different kinds of molecules, different kinds means not by the structure, means they are all the polymer molecules, but they have different molecular weights, because you know there will be species of different molecular weights and you are taking the average of these molecular weights and you are determining Mn, say in this case. So, let me write down the expression and then I will explain. So, this is sum over Ni Mi divided by sum over Ni. So, this means you are summing over all i's. So, maybe you may have N1 moles of molecules which have molecular mass M1, you have N2 moles of molecules which have molecular mass M2, like that. So, you are summing up. So, suppose you have 10 kinds of molecules of molecular weight M1, M2, M3 up to M10 and the corresponding number of moles are N1, N2, N3 up to N10, then this is the summation. The total weight is basically number of moles into molecular mass and then you sum it up and divided by total number of moles. Okay. Now, this is the expression of Mn. If you are trying to have an expression of Mw, weight average molecular weight. So, if you are looking at Mw, then what is the expression of Mw? It is Wi Mi. Now, do not confuse this Wi with this Wi. This is the weight fraction of molecules having molecular mass. So, weight fraction. So, if you have 10 kinds of molecules, so weight fraction of molecules. So, if you have 10 kinds of molecules, so the weight fraction of molecules W1 which have the molecular weight M1, weight fraction of molecules W2 which have the molecular weight M2, so on and so forth. So, if you add them up together, then you basically have your molecular weight, which is the weight average molecular weight. Viscosity average molecular weight will come afterwards. So, let me give you an example of this. Suppose you have a polystyrene sample. I am just trying to work out a problem here. So, suppose you have a polystyrene sample and this polystyrene sample is composed of this, say 1 gram of polystyrene which has molecular weight of 10,000, 2 grams of polystyrene which has molecular weight of 50,000, 3 grams of polystyrene which has molecular weight of 100,000. Now, these are not exact molecular weights, of course. There is something called polydispersity. So, which means if the polydispersity index which is defined by Mw by Mn, if this is higher than 1, the more the value, the more is the dispersity. That means, the more is the distribution of the molecular weight among different polymer chains. If this ratio is 1, that would mean all the polymer chains have actually the same length. So, So, this in practice is never 1, but this can be close to 1 by different controlled processes you can actually create polymers which are close to 1. So, still you are actually talking about average, but the molecular weight is very narrowed down, the dispersion, the distribution of molecular weight. So, they are you can tell they are fairly monodispersed samples. So, polystyrene sample, so you have 3 fairly monodispersed samples of 1 gram of 10,000, 2 grams of 50,000 molecular weight and 3 grams of 100,000 molecular weight, and then we mix it up. So, then the question is, in this particular sample with all these 3 together, what is the value of Mn, that is number average molecular weight, what is the value of Mw, weight average molecular weight, and what is the value of PDI, that is polydispersity index. We will talk about it little bit later. Now, I am going to give you the formula. This is the formula, Mw by Mn is the formula. Now, Mn, Mw. So, in order to determine this value of Mn, so it is total weight divided by total number of moles. So, total weight is 1 plus 2 plus 3 divided by total number of moles. So, this is 1 divided by 10,000. So, 1 gram. So, number of moles is this, plus 2 grams divided by 50,000 plus 3 grams divided by 100,000. So, this value I have not actually calculated, you can calculate actually. So, this is the value of Mn that you will get. So, what is the value of Mw? I am trying to work out this problem in order to give you an understanding about the formula that I have drawn, and try to understand what is the significance of that formula in terms of the problems here. So, Mw is the sum over all the weight fractions corresponding multiplied by Mi, which is the molecular weight. So, the weight fraction, so total weight is 6 grams. So, weight fraction of the first sample is 1 divided by 6, that multiplied by the molecular weight 10,000. So, like this you add all of them up, 2 by 6 into 50,000 plus 3 by 6 into 100,000, and then you get the value of Mw, and the polydispersity index is basically equal to Mw by Mn, that you can work out. So, I have given you the expressions of number average molecular weight, weight average molecular weight, and worked out a problem for you which gives you an understanding of how the things basically work, and if you have these kind of problems, how do you solve some of these things. So, what now is the time to conclude this particular class. So, before conclusion, I am trying to give you a prelude of what is going to come in the next class. In the next class, I will actually talk about how you can determine Mn, this number average molecular weight, and there you will see that we basically rely on colligative properties of the polymer solution. Now, you know these colligative properties, they actually depend on the number of particles of the solute present in the solution. And so, these kind of experiments that you do, they are biased towards the low weight fraction part of the sample, because your sample, as I told you, can have say 90% of polymer molecules which have very high weight, or maybe 10 weight percent, rest of that may be of low weight. So, basically some of the experiments that we do, colligative properties are one of them, you can talk about Mw also. Some of the different experiments that we do for the molecular weight determination, some of them are biased towards low molecular weight fractions of the polymer sample, and some of them are biased towards high molecular weight fractions of the polymer sample. And you will see, as you can understand from the what I have told already, colligative properties that depend on the number of particles. So, they basically are biased towards the low molecular weight fractions. So, we will conclude here, and we will start with the different experimental techniques to determine the number average molecular weight in the next class. Thank you.